This video is the fifth in a short series on antiderivatives and indefinite integrals, and this time we're going to discuss antiderivatives that result in the basic trig functions. So all we're trying to do here is recognize the derivative formulas backwards for the basic trig functions sine, cosine, tangent, cotangent, secant, and cosecant. So here's our standard list of formulas for these derivatives. The derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant squared, cotangent, that gives me negative cosecant squared, secant, that gives me secant times the tangent, and finally cosecant, that gives me a negative cosecant times the cotangent. This list of 6 derivative formulas can be used to quickly make a list of 6 antiderivative formulas, where we're just looking at the antiderivative of the right-hand side of each of these equations. But there's a subtle distinction here. When we make this list of standard formulas, we're not going to include the minus signs that occur on half of these derivative formulas. So for example, in number 2, I want the indefinite integral or antiderivative of sine x, not negative sine x. So we're going to have to adjust for the minus signs for those 3 formulas, but otherwise it's a pretty simple process. If the derivative of the sine function is equal to the cosine function, then the antiderivative of cosine, that just means the thing you differentiate to get the cosine, well, we're just looking right at the answer. That's sine x. And we have to include an arbitrary constant of plus c on there, so we're being as general as possible. Now, what about the antiderivative of the sine function? You could imagine taking this derivative formula and simply multiplying both sides by -1. And now we see that the thing you differentiate to get the sine function is actually the negative of the cosine function. So I get negative cosine x plus c. And we go on like this. The antiderivative of secant squared is just the tangent function. The antiderivative of cosecant squared is negative cotangent, where again, I'm just compensating for that minus sign. The indefinite integral of secant times tangent, well, that's the thing you differentiate to get secant times tangent, so that's just the secant function. So I have secant x plus c. And finally, the integral of cosecant cotangent, that's just the negative of the cosecant function plus c. So these are our 6 antiderivatives resulting in the basic trig functions. And we'll wrap things up with a few quick examples. So in the first one, we're asked to compute the function little f of x such that f prime of x is equal to 2 sine x. In other words, we want the antiderivative of 2 sine x, and we have an initial condition on this. We want f of 0 to equal 1. So this is not just about guessing the antiderivative to 2 sine x. We're actually solving a small differential equation here. F prime of x equals 2 sine x, and it's called an initial value problem because we have some initial value given to us. And I'll post a link to a previous video in this short series where we talked about initial value problems. So the first thing I want to do here is figure out the most general antiderivative. So we're trying to find the thing that differentiates to 2 sine x. And 2 cosine x is close, but we'd miss by a minus sign. So be careful about the minus sign. I get negative 2 cosine x. And you can always check your answers when you're trying to guess antiderivatives. You just imagine taking the derivative of this thing, and the derivative of cosine is negative sine, and the minus signs cancel, and it all works out. And again, to be as general as possible, I have an arbitrary additive constant. So there's the function I differentiate to get 2 sine x, but I also want to apply this initial condition, f of 0 is equal to 1. So f is equal to 1 when x is equal to 0. That allows us to find the arbitrary constant. Recall that the cosine of 0 is 1. And then I'll add the 2 to both sides, and I end up with 3 equals c. Finally, we plug in that value for the arbitrary constant back into our general solution, and I end up with a negative 2 cosine x plus 3. And that's the unique function that satisfies the differential equation, f prime of x equals 2 sine x, and passes through the point 0, 1. In the next example, we want an indefinite integral of a cosecant cotangent. This is basically just quoting the formula. I know this essentially comes from the derivative of the cosecant function, but that the derivative of the cosecant produces a minus sign. We make sure to include that out in front. And don't forget the arbitrary constant, and we're done. Finally, I have an indefinite integral that requires a little bit of manipulation before we apply our basic antiderivative formulas. I have the secant of x multiplied by the quantity secant x plus tangent x. And what I notice here is that if I distribute the secant into that quantity, good things are going to happen. I end up with a secant squared x and a secant tangent. So secant x, tangent x, dx. So we need to get the antiderivative of each piece of this, and the antiderivative of secant squared is just the tangent function. Again, this is just because the derivative of the tangent function is secant squared. And then secant multiplied by tangent is another standard formula. That's the derivative of the secant function. So our antiderivative here is just secantx. So we end up with tangent x plus secant x plus an arbitrary constant c, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zax Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zax Lab, and best of luck on your math and physics journey.